Hello guys, and welcome to a new video in the Graphs and Networks video series. Today we will be discussing about graph connectivity. So this is going to be a theoretical video. We will be discussing about some definitions and how we use that to exactly define connectivity of graphs and deal with it. Okay, so let's go over some definitions first of all. So first of all, you have something known as a walk, that is generally denoted by capital W. So a walk is a sequence of alternating vertices and edges in a graph. So it's denoted by W is basically your U0, E1, U1, E2, U2, and so you follow that pattern on and on till you get UI, EI, and you still follow that to get UN, that is your last vertex. So this is generally called a walk. It's basically a sequence of alternating vertices and edges. And an important note in a walk is that you can repeat your vertices and you can repeat your edges. So vertex repetition is allowed and edge repetition is also allowed. So walk can also be written as like U0, U1, U2 up to UN, because for each edge there always exists two end vertices. Okay, so you can skip the edges in between. You can just write U0, U1, U2 up to UN. So there are two types of walks. If your U is equal to V is basically your UN, that's just another name for UN, and U is basically your U0. So if U is equal to V, or in other terms U0 equal to UN, then that means that your walk is a closed walk. That means that you have ended at the point where you have started from. Okay, and if U0 equal to V, it's known as an open walk. Okay, so let's illustrate with the help of an example. You see in the diagram you have got 6 vertices all marked in red, and you've got the edges marked in white. So an open walk, and one example could be U1 to U2 to U4 to U3 to U6 to U5 and back to U4. Okay, you see that our starting vertex was U1, our ending vertex is U4. So this is an open walk, and you can see that I have repeated the edges U4. Okay, so edge repetition is allowed in a walk. Okay, so an example for a closed walk could be U1 to U6 to U5 to U4 to U2 to U3 to U6 and back to U1. So that's my walk. You see that my starting and ending vertex is the same, and I've also repeated my vertices. So I've got, you see that U6 has been repeated. Okay, so that's an example of a closed walk. So these are not the only examples for open and closed walks. You can have many examples. Okay, I just illustrated a random one for example purposes. Okay, so second definition is known as a trail. So trail is a walk where no edges are repeated. So if you remember, in a walk your vertex repetition is allowed and in your edge repetition is allowed. So this is for a walk. For a trail, only vertex repetition is allowed, so no edges are repeated. Okay, and a trail by default is an open trail, and when you have a closed trail, people generally call that a circuit. Okay, so we'll also follow that convention. So closed trail is called a circuit. Okay, so let's just take the same example, same graph as shown above, and let's illustrate a trail. So a possible trail could be U1 to U2 to U3 to U6 to U1 to U5 to U4. Okay, you see, like you can see that this is an open trail, as your starting vertex and ending vertex aren't the same. Also, if you like pan it out on a piece of paper, you can see that I have not repeated any edge. Okay, any like all the edges are unique, but you can have vertex repetition as it is observed by having U1 here and here. Okay, so vertex repetition is allowed, but you're not allowed to repeat your edges. Okay, so circuit, which is basically a closed trail, can be like this. So U1, U2, U4, U3, U6, U5 and U1. So our starting and ending vertices are same and no edges have been repeated. So this is a closed trail, also known as a circuit. Okay, so and the next definition is a path. So path is a walk where no vertices are repeated. Okay, so edge repetition is allowed, but like basically your vertices should not be repeated. Okay, so no vertex repetition. So path by default is an open path, and a closed path is generally called a cycle. Okay, so let's just take the same example again. So a path could be u1, u2, u3 and u6, and a closed path, that is a cycle, is u1, u5, u6, u1, u5, u6. Okay, so and back to u1 again, obviously, because it's closed path, and that's the circuit. So there are some remarks. So basically I've drawn two diagrams here. Let's see what these mean. So for the first diagram, you see that every path is a trail, right? So every path is a trail, because path is a subset of trail. Basically, mathematically, path is a subset of trail, and trail is a subset of walk. Okay, so every path is a trail and every trail is a walk, but vice versa need not be true. Okay, so that's basically your first diagram. Your second diagram means that every cycle is a circuit, because it's a subset of a circuit, but every circuit need not be a cycle. Okay, that's what it means. Also, the length of a UV walk is the number of edges in that particular UV walk. So you write down the walk as, say, W is equal to U0, U1, U2, U6, U5 and so on, and say you end up at U3. So U0, U1 comprises of one edge, U1, U2 comprises of another edge, and you keep counting them until you reach U3 and just add them all up, and that'll give you your number of edges in that particular walk. Okay. So the distance between two vertices u and v is the length of the shortest path from u to v, denoted by d of u comma v. So this particular relation of d is an equivalence relation, and the shortest path from u comma v is called the distance between those two vertices. Okay, so a graph G is said to be connected if there is a walk between any two vertices. So up until this particular video, you've been hearing me saying that this graph is connected. So in its very essence, a connected graph means that for any two vertices, there is a walk in between. Okay, so that's what it means. What do you mean by a connected graph? And a disconnected graph is a graph that is not connected. Basically, you just negate the definition of a connected graph to get a disconnected graph. Okay, so in a disconnected graph, the connected subgraphs are known as components. Okay, and components are denoted by k of g, or sometimes people call this as kappa of g. Okay, so if k of g is greater than 1, equal to 1, greater than equal to 1, then that your graph is connected. And if k of g is strictly greater than 1, then that means that your graph is disconnected. Okay, so I've got 3 examples here. So obviously in my first example, you see that I've got 2 examples. Sorry, my bad. This is example 1 and this is example 2. In the first example, you see that you've got 2 cycles joined together by a vertex in your upper part and C3 in your lower part. So this is a disconnected graph. So this forms one component, this entire thing, and this forms the other component. So this is a disconnected graph and it has 2 components. In this example, you see that this is a connected graph, and by connected I mean that if you pick out any 2 vertices, any possible combination, you will see that there exists a walk between these 2 vertices. Okay, so that's what you mean by connected graph, and since it's connected, you can see that it only has one component. Okay, so to summarize, we first learned about 3 things: a walk, a trail and a path. And in trails you have 2 different things. If it's open, it's known as a trail by default. If it's closed, you have a circuit. In paths, you have learned that if it is open, it is by default a path, and if it is closed, it's known as a cycle. Then we talked about the precise meaning of connectivity of graphs. What do you mean by connected, disconnected graphs? And you talk about the components for different types of graphs. If it's disconnected, your kappa of g or k of g is always greater than 1, strictly greater than 1, and if it's connected, your k of g is greater than equal to 1. Okay, so that was the summary of this video, and that's it for this video, guys. Hope you liked it. Make sure to like, share and subscribe, and check out the other videos in the playlist as well. I'll put the I banner on top, and yeah, I'll see you guys in the next video. Bye bye.